Okay, so first of all, I want to thank the organizer to giving me the opportunity to be here today to talk about my work, and specifically, I will give a talk which is in continuity with the previous one. Somehow, I will tell you something more about the phase diagram of high pressure hydrogen. So this, as Carlo said before, is a very long time challenge which started in 1935 with a prediction with the hypothesis of Wigner and Huntington that it was a phase, a metallic phase of atomic hydrogen, which was hypothesized to be stable over 25 GPa. But interest in this problem, as all we know, I assume, rose in 1968 when Ashtorff actually predicted this phase, this atomic metallic phase of hydrogen, to be a high temperature superconductor. And I think that we are all here today because we have there was a very big success, which I call experimental success, which was the synthesis of actually a high temperature superconductor made of hydrogen anhydride, which is H3S, which broke the record held by cuprates for more than 40 years, for about 40 years. And they broke for almost 70 Kelvin, which is really a remarkable result. And I think that since 2015, the attention on hydrogen really rose and brings us today. But this challenge on metallizing hydrogen is much more difficult than what originally expected, because it's not at all, not even close to 25 GPa, the pressure required to reach this pressure. So in this presentation, I want to focus on the low temperature phase diagram of hydrogen, as also Carlos showed you before. This is a very schematic sketch, and we actually do not know very well what's happening between 300 and 500 GPa, and where this atomic, this holy grail for us physicists, this atomic phase will be stabilized, if it exists or not. And the reason why there is so much confusion is, as also Carlo mentioned, that we have a lot of different experimental results that seems in contradiction, at least apparently. So for example, there is the experiment from Ranga Diaz and Silvera, which is a remarkable result in which they show that at 495 GPa, hydrogen starts to be highly reflective, and so this could be actually the first time we see the metallic hydrogen. But then there is another experiment by Paul Aubert published in 2020, which also Carlo mentioned, in which they see, by looking at infrared absorption spectrum, that they see this sharp transition at about 420 GPa, in which the system stops transmitting infrared light, and they assign this to a metallization, which is reasonable. And then there is the experiment by Mikhail Heremets, which actually measured the conductivity and say that at about 360 GPa, we have the onset on conductivity, and then track conductivity up to a bit higher pressure, which increase. So this here is resistivity. So resistivity decrease means higher conductivity with pressure. And so here we have a very puzzling result. So let me a bit recollect all this in this qualitative phase diagram here. So we have this phase 3 that at 360 GPa starts conducting. And so we have an onset of conductivity. But if you look at the infrared spectrum, it remains transparent in the infrared spectrum up to 420, when suddenly becomes opaque. And if you look instead optically by just making photos of the picture, you see that you have a transparent spectrum. This phase is transparent below 300 GPa, then start darkening, becoming reddish, and then black. And it remains black up to 490 GPa, when it was observed to be shiny again, and not to be shiny. And so what actually is happening here? So you see these results seems to be in contradiction between them. And there is some issue also in pressure calibration, but it actually is not enough to explain the difference between these difference. For example, if you correct for pressure calibration, these two lines gets even farther apart. So this mismatch with pressure is not just a problem of pressure calibration. And so this is a very good opportunity for me and for us theoreticians to try to say something, try to do some prediction to see what actually is happening. And because, as Carlo mentioned, hydrogen is in principle the simplest element we can simulate. However, it's a very challenging problem because actually we require an accuracy in comparing energies of different phases to predict the phase diagram below 1 milli-electron-volt per atom, which goes beyond the DFT accuracy. And indeed, the other problem is that hydrogen is also the lightest element in the universe, and the quantum fluctuations are really sizable, and I will show them in the next slide. And they are so big that we have huge anharmonic effect even at 0 Kelvin, which completely reshape the phase diagram, as I will show. So to tackle the problem, what we did was using diffusion Monte Carlo, and we also relaxed the fixed node approximation to actually get even better energies. And we corrected finite size error studying systems bigger than 1,000 atoms, that for as long as I know is the record in hydrogen right now. So we really pushed toward the accuracy to predict a very good energetics for the static phase. And then to study phonons, to study the anharmonicity, we used the anharmonic theory, the self-consistent harmonic approximation, which is an anharmonic theory, which allows us to predict anharmonicity and quantum fluctuations at DFT level. We use the DFT belief, which is one of the best functionals, and for hydrogen. And so these are the phases we considered. Most of them have been predicted by Chris Pickard, for example, and the three of them which I'm going to talk, also C2C24, which is the candidate for phase 3, CMCA 12, which was proposed as another candidate for phase 3, and CMCA 4, and these all three, I think, were predicted by Chris. And so then we have the candidate for the atomic phase. And here the gray dots you can see are snapshot of the quantum probability wave function of nuclei. And so that's why I say that quantum effects are sizable, because you can see them by eye. So as you can see, hydrogen, even at 0 Kelvin, are not static at all. And so to go to the main slide of my presentation, this is the phase diagram we were able to simulate by coupling diffusion Monte Carlo with this anharmonic theory that is the self-consistent harmonic approximation. So this is hydrogen. I plot here the enthalpy of each phase versus the pressure, and the phase that is stable at each pressure is the phase with the lowest enthalpy. Each phase has a finite line width, which is the error of finite size effect on the diffusion Monte Carlo calculation. And as you can see, what we find is that below 410 GPa, this most stable phase is C2C24, which is phase 3. Then we predict a phase transition to another phase, which is the CMCA 12, which we call phase 6. And then only at a much higher pressure than what was taught before, at 577 GPa, this phase 6 finally transforms into the atomic metallic hydrogen. And the reason why the atomic metallic hydrogen is stable at much higher pressure than even taught before is due to the anharmonicity on the quantum fluctuation. And you can see here, this is what also Carlo was showing before. If we neglect phonon fluctuations at all, the atomic structure is not even present up to 700 GPa. If we include quantum fluctuation at harmonic level, then this phase 6 is completely canceled out by the phase diagram, and we have just a transition between phase 3 and directly the atomic phase at about 486 GPa. But then anharmonicity push up again the atomic phase and makes the phase 6 stable again. The other important result to take home from this slide is that we also were able to simulate deuterium, and so the isotope shift. And for example, we predict that there is a quite remarkable isotope shift for the atomic simulation, so which goes even to 640 GPa in deuterium, the transition, which is quite far and probably quite difficult to reach in the very near future. But for deuterium, for the phase 3 to phase 6 transition is actually way better, because it's 442. So just 32 GPa of isotope shift. Now remember this number, 32 GPa, because it's interesting, and we will see later why. So as also Carlo mentioned, the main point here is, okay, we predicted the phase diagram, but there are a lot of ways of predicting phase diagram. How can we sure that this is the exact one, this is the correct one? And the answer to this question is we need actually to predict which are the experimental signatures to each one of these phase transitions, to compare with the experimental data we have, and to propose eventually new experiments to confirm this. And so the best way to do this is optical experiment, for example. And we predicted the optical properties of the system. And as you can see, this is phase 3. So we predict by accounting for quantum effects, also the indirect gap, which is this line here, which we show it closes at about 370 GPa, which is in quite good agreement with the onset on conductivity observed by Michaela Hermetz and group, and which can be seen here. Which so we are able to. So what does it mean? It means that actually the onset of conductivity observed experimentally is not a phase transition, slightly speaking. It's still phase 3, but we have just the band gap that is closing with pressure. Then the optical gap, which we measured by measuring the transmitted spectrum, so exactly like it is done in the experiment. So we measure transmittance on the sample and just take where the instrument precision, is not able anymore to see anything. And we say this is the optical gap. And it's in very good agreement also with the data from Laubert, up to a certain point when Laubert observed this drop here, and we will see this later. And this drop, we can prove that is associated to the transition to the phase 6. And actually, we can measure again the transmittance of phase 6. This is the CMCA12. And what we observe is that the transmission dropped before the C2C24. So this is at 355 GPa, and already at 355 GPa, the CMCA12 is almost completely dark. So this means actually that if you want to see a transition between phase 3 to phase 6, actually in the infrared light, here this optical spectrum, you can see a drop of the transmitted light, exactly like it's observed in the Laubert experiment. And the pressure agrees remarkably well. We observe 410 plus or minus 20 GPa, and you observe 425 GPa, so it's quite good, the agreement. We can propose an alternative way of measuring this phase transition, which would be very good if we can have experimental data on this, which is a jump in the conductivity. So we expect that on the transition, conductivity, static conductivity will increase by a significant amount. And this could be measured because conductivity measurements at similar pressure are already available. And so I think this is something that probably will be available in near future and will be an independent way of proving that actually there is a phase transition to phase 6. Then the point is that one of the points is that as I show you in the previous diagram, if you look at the optical spectrum in the visible light, you don't see any difference between phase 3 and phase 6. And this is can be seen here. So at 460 GPa, for example, the reflectivity for the C2C24 and the CMCA12, which are phase 3 and phase 6, are almost identical. And they appear, here I made a photorealistic rendering by just integrating the optical equation with the simulated refractive indexes, imaginary and real refractive indices of the phases. So you can see here that this appears as a black metal, as a black metal, and as we increase pressure, we start increasing a bit the reflectivity, but not so much that is really visible until really high pressure when we transit into the atomic phase, which is this one here, when the sample start shining. So actually, looking at the reflectivity is a good way to detect the atomic transition, and the problem is that our pressure do not agree very well with what observed by the experiments. And so now I told you that we are able also to do the isotope shift, and we have an isotope shift between the phase 3 and 6 of 32 GPa. And last week, Paul Aubert published finally a paper, so in which he remade exactly the same experiment, but with the deuterium, showing a isotope shift of 35 GPa. And so this was a prediction, because our paper work on archive was on archive already on January. So our prediction agrees very well with the data. And so this is a remarkable result, I would say, which makes the data even a bit more trustable. And so that's why I'm really confident that this phase diagram is actually a very good one. Yeah, I have finished. So to summarize a bit what we have done, so we predict the existence of phase 6, which is CMCA12 above 410 plus or minus 19 GPa. And this phase transition can be detected experimentally looking at low energy excitations like infrared optical spectrum or DC static conductivity measurements, which would be another proof of this phase transition. And we predict a 32 GPa of isotope shift, which is in very good agreement with and confirmed by experiments very recently. And for the atomic transition, we predict this phase transition to be stable at much higher pressure. And this is a robust result, we think, because with respect to harmonic, the reason why the pressure is so high is essentially that an harmonicity lower a lot the vibrational energy of the H2 molecule, while in the atomic hydrogen is much more harmonic. So when an harmonicity is taken into account, it favors molecular phases. And therefore, the transition to the atomic phases is shifted to higher pressure. So that's the reason why. And so reflectivity measurements are a good way to detect this phase. And so it remains an open question is, what is the phase observed, reflective phase observed at 500 GPa? And this is a very interesting question, because maybe another phase exists, which could be even superconductive, we don't know. So this is an open question, and I think it would be very interesting to investigate.
Thank you very much.